Welcome to the October Sky Project Lab 1 Components and Design tutorial. What you're about to see is pretty cool. This is a free online program called Open Rocket. There's a link for it on the lab. Just a reminder to those of you who have Macs, you're probably going to have to go to security and privacy again to allow this app to be opened. But I use it every year. It's very, very safe. There's nothing, no viruses in here. Once you get this opened, it is going to allow you to design your own rocket with the exact specifications of the lab kit that you received from school. And this is pretty cool because it allows you to simulate the launch of your rocket to see what makes it go the highest without actually having to launch it a bunch of times before our our launch on Fiesta Island. So you basically get to know, is this rocket safe? Does it work? And will it go to an adequate height before you even, launch it all together at our exhibition? Okay. Just a note, the first part of this lab, where it says part one, explore the components of a rocket. I'm not going to go over that. It's pretty self-explanatory. You just go to the website or any website on model rocketry and basically teach yourself a little bit about the different components of a rocket. But once you're aware of those different components, you can go ahead to, the Open Rocket section of the lab, which starts on part two, where it says design the first draft of your rocket using Open Rocket Simulator. All right. And what you're going to be doing is you are going to start with the nose cone. Okay. Building your rocket begins with a nose cone. So I'm going to go ahead and select that. And there's several different shapes. Conical means just the nose cone looks like a pure cone. You can kind of see here, right? Pure cone. There's ellipsoid and there's ogive. I'm just going to go ellipsoid just for funsies. Okay. And the length of 15 centimeters is quite long. What you're going to want to do is actually measure the length of the nose cone in your particular rocket kit. Okay. And I don't have one in front of me, so I'm just going to pick, let's say, 8 centimeters for fun. Okay. And the base diameter of my nose cone is, for this lab, most of you, if not all of you, are going to be using the NC60 body type, which has a very specific diameter, a diameter where the outer tube is 4.16 centimeters and the inner tube is 4.05 centimeters. Okay, so that means that the base diameter of this nose cone has to be equal to the outer diameter of the tube that you're using, which is 4.16 centimeters. Okay, and the wall thickness for the nose cone isn't too important for this, but I'm going to go ahead and say it's about 0.1 centimeters or a millimeter thick. That's roughly correct. It is definitely not made of cardboard. It is made of, the closest material is acrylic. It's a type of plastic. And yes, it will be painted, and that, to a good approximation, that's about the thickness of the paint. Okay. Now, if our nose cone looks just like this, there's no piece of it that can actually slide into the body tube, so we need what's called a shoulder as well. And a shoulder length of just about 2 centimeters is fine. It doesn't have to be too much longer than that. But the diameter of the shoulder has to be equal to the inner diameter of the body tube, so it fits in just perfectly snugly. And we said that the inner diameter of the body tube is 4.05 centimeters. Okay? And again, the thickness can be just 0.1 or 1 millimeter. All right? Okay, and so we can go ahead and say close. And now we have a full nose cone. Okay? We have this little shoulder here. You can see the diameter of the shoulder is a little bit less so that it slides into the tube and it's able to be secured. Okay, very cool. We have that down, our NC60 nose cone inside the program. Now we want to add a body tube. Okay, so we, of course, go over here to click on body tube. First question is, how long is it going to be? Well, your lab kits come with two 18-inch long tubes and a coupler. So in other words, there's like a little tube that you'll notice can bind um, the two smaller, or sorry, the two body tubes together for a total of a possible 36 inches. All right. Now, it doesn't have to be that long. If you use the full length, a long rocket is kind of impressive looking. Shorter rockets, however, can serve on mass and will go a little bit higher. So it's all about you to decide. I'm just going to go ahead and pick, let's say, I don't know, a half a meter. So let's go 50 centimeters for my body tube length. Okay. And the outer diameter, remember we said is 4.16, right? And the inner diameter is 4.05. Okay. Now, what does that say about the wall thickness? Well, if the wall thickness has to be the difference between the outer and inner diameter divided by 2, because one full diameter includes 2 walls of the tube, right? So the difference between these is 0.11. Divide that by 2, you get 0.055. So that must be the wall thickness of our body tube. As for what it's made of, it is made of cardboard. So this works for this. And yes, it will be painted. So we can leave that alone. And now we can just click close. And boom, we have the body tube of our rocket. Cool, right? All right, what's next? Well, next we have to make sure that we can put an engine in here, right? There's going to be these high-powered combustion engines that thrust these rockets up into the sky. So we need to make a body tube. All right. So to make a body tube, you need to add an inner tube. Okay, which we just did. You see, it shows up over here. Cool. Now, the outer diameter of the body tube has to be the diameter of the engine we're using, which is a D engine, which is 2.4. Or sorry, this has to be the inner diameter, right? Because it's got to fit inside there. So 2.4. And the outer diameter, oh, why is it doing that? Okay, so outer diameter is going to be, this is actually in the lab, 2.46. So that this can be 2.4. And then that gives you a wall thickness of about 0.03, which is true for our engine mounts. So why did I do this again? Okay, the inner diameter has to snugly fit an engine that's 2.4 centimeters in diameter, right? Obviously, the tube has to have some thickness, roughly a third of a millimeter thickness, and that's going to create an outer diameter of that tube of 2.46, right? Coincidentally, it picks the exact length of the engine for us, so that's 7 centimeters, so that's good. And now, what should its position be relative to the bottom of the parrot component? The parrot component just means the big body tube, and it should be 0 offset from the bottom of the tube, right? Like you don't want this to be here or outside, right? But you want it to be snugly fit right along the alignment. So that's 0 centimeters. And then also this is going to be made of cardboard, so we click OK. Cool. Now, as it stands right now, we got a couple issues. One issue is it's just floating in there, right? This is, ding, 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 ding. It's just totally floating, right? And it's not secured inside there. So what you need then is centering rings, okay? And this went ahead and made one for us, right? The centering ring is going to have an inner diameter and an outer diameter, right? The inner diameter needs to be the same as the diameter of this so that it holds it, right? Because it wants to secure this engine mount in it, right? But it wants to secure that engine mount to the diameter of the body tube. So the inner diameter has to be the diameter of the actual engine mount tube. And the outer diameter has to be the diameter of the body tube itself, right? Okay, so that it basically, bridges the gap between the engine mount itself and the body tube. Okay, so that's cool. and we want it to be offset by 0. But so I'll just leave that one there. But we need another centering ring too, because just having one, that's not going to be too stable. We want another one down here, right? So I'm going to pick another centering ring. I want it the same exact size, but now I want this offset from the bottom of the parent component of the body tube by about 7 centimeters. So I want it 7 centimeters behind the end of the tube. So that's -7. That's 7 behind the end, right? So it's -7. And if I click close, you see now I have 2 centering rings. And now this guy is bound in here wonderfully, right? Okay, but we still have another problem with this engine mount. Anyone guess what it is? 5, 4, 3, 2, 1. Hopefully you guessed. Maybe you didn't. If we put an engine in here, what's keeping it from flying through into the middle of the rocket, right? And burning the thing from the inside out. This is the biggest mistake that students make. And so to avoid this, you need what's called an engine block, right? Which basically is a little block. So it has to be the diameter of the inner tube, which again is 2.4 centimeters, right? And it's going to have an inner diameter of, the wall thickness of these guys is a little bit thicker because it's got to be kind of strong. So let's make it 0.3 centimeters or 3 millimeters. Okay, and the length of about a half a centimeter is good. That's fine. But the position relative to the parent component again is going to have to be -7, because we need this thing over here right at the end of, we need to glue this right inside this tube at the end here, so that when the engine's put inside here, this blocks it, right? This keeps the engine from flying through into the middle of the rocket and burning the rocket from the inside out. Okay? Now, everyone, we have a very successful engine mount. Okay? And remember, this has to be glued inside this body tube. Okay, so what's next? Well, next we got to create some fins, right? And so there's a couple options here. You can go ahead and just make your classic trapezoidal, right? And that looks like these guys. But you could also make your elliptical, but you could also do freeform. I'm going to do freeform because it gives you the option of adjusting your fins to be however you want. You could pick trapezoidal or elliptical if you want. I'm going to pick freeform. So I'm going to delete that and I'm going to go back to freeform over here. And I want, we could typically do either 3 or 4 fins, right? 3 fins will get you a little bit higher. 4 fins will create a more stable flight. I'm going to leave that up to your choice. I'm going to go ahead and pick 4 for funsies, okay? And again, I don't want to offset from the bottom, although we could, and you could have fins that are higher up in the body, but I'm going to do 0 here, okay? These guys are going to be made of basswood, okay? And the thickness is, I would say 0.3 centimeters is accurate for, or 0.25, but this is fine. Now the cross section means, is the top of the fin going to be totally square? Or are you going to round it, or are you going to make actually like a little edge, sand the edge so that the top's at a straight angle? Let's say that we'll all round the tips of our fins, right? Okay. So now what's the shape going to look like? Oh, look at this cool thing. We get to actually adjust, right? And make exactly whatever shape we want. And so, all right. So that's kind of cool. And so I can double click, I can add another thing here. So let's say I do something funky and make four fins like this, okay? So I'm gonna click close, and now check this out. I have these 4 fins attached to my rocket. This is really coming together. At this point, I'd like to point out these 2 little symbols here. These are so super important. This is the center of gravity, and this is the center of pressure. Center of gravity is the center of mass of the object, right? Basically the balancing point. Like if you put your finger right there, the rocket would balance right there, okay? The center of pressure is the average location where all the drag is applied to the rocket, right? So obviously you got a lot of drag acting here on the fins, lots of drag there because of the fins. That's why the fins are there to create the right amount of drag to create a stable rocket. You also have some drag up here at the nose cone, right? But if I was to average all the drag, all the force of all the drag over the total rocket, the average is about right here. Now here's the thing. This always has to be lower than or behind the center of gravity. If this ever exceeds and shows up over here, then you have an unstable rocket. Okay, and an unstable rocket is actually dangerous. You don't want this at the exhibition. Okay, so as you're designing this, look at for these two numbers very carefully and make sure the center of pressure is behind the center of gravity. If it's not, then the drag creates a torque which turns the front of the rocket one way or the other, and you get whoosh, or whoosh, instead of nice flowing smooth motion upwards. Okay. All right. That's fins. What's next? Well, we got to create a launch lug, right? In other words, we got to create something so that the rocket it can stand stably on the launch pad, and for that you use this little guy, a little launch lug, right? Length doesn't really matter. 3 centimeters is fine. You could actually measure the one in your kit. Actually, that would be the best. There's one of these in the kits, and you could measure it and see what the size is. The inner diameter has to be bigger than 1/4 of an inch, right? So you can also measure that in your lab kit, but I'm going to leave this the way it is for now. It's also made of like a cardboard-like material, and we're going to click close. And the one thing that's important is that the position needs to be roughly where the center of gravity is. And I see in this case that's already happened, so I'm going to leave it there. But you can always adjust this here if it's not showing up where you want it to show up. Okay, but it already has, just by pure luck, showed up there. So I'm going to click close. Now I have a launch lug. I can put this over the rod of the launch pad now, and that's good. Okay, next. This thing is going to fly up in the air. We want to be able to use these many, many times, right? So we want a recovery system. We want a parachute. So I'm going to go ahead and click a parachute. Part 4 of this lab, which we'll do in 4 weeks, you guys are actually going to calculate what the diameter should be for your particular rocket. For now, 30 centimeters is a good approximation. 6 shroud lines is what you're going to be using. That's all fine. Great. It already has the elastic cord attached into it, so that's fine. If this elastic cord is here, you don't need the shock cord. There's a question further in the lab that tells you to add shock cord. If this is selected, you don't need to do that. And we want to know when this deploys. Well, usually we set it at about 5 seconds. So after the engine's done burning, there's going to be an ejection charge that shoots out the parachute after about 5 seconds. Now, a couple more things. We see over here that the parachute isn't quite filling the body. We obviously want the parachute to fill the body. It's going to fill the body. So the diameter of the packing should be the inner diameter of the tube, which again is 4.05. And then we also want it to be, we don't want it to be right over here overlapping with the shoulder of the nose cone, right? It's gonna get caught on and that's just ugly, right? So we need this to be packed a little bit deeper. Let's say 10 centimeters deep. That's fine. And then, oh, look at that, perfectly. We have a parachute now inside of our rocket. Whew. All right. What else do we need here? What else are we missing? Last thing is shock cord. Again, we don't need that. So that brings us to motors. Okay. Now, to add an actual motor to this, which, by the way, you're not going to have in your kit. I'm going to be bringing that to you at the rocket launch. But you want to go over here to motors and configurations, okay? And you're going to want to, next up, you want to select inner tube. Select inner tube over here. And then this comes up and we want to do new configuration. Okay. And so for this new configuration, we want to select a motor And specifically, we want to make sure only Estes is selected, right? We're using Estes motors. And in particular, we're using the Estes D engine D12. Um, that's, it shows you the diameter that I said that it was and the length 7 centimeters, right? So we're selecting that, okay? And ejection charge delay, we said was 5 seconds. So we're going to put 5 seconds there. And I click OK. Cool. And now we're actually loaded with an engine. How cool is that? All right. All right. Now we are ready to actually simulate the flight of this rocket. So assuming this is exactly the rocket that you design, right, within your lab kit, now we want to see what is it going to fly like. So I go to flight simulations over here. Okay. I first want to do a baseline simulation. Like, if I don't change anything about this rocket, what is it going to do? So I go to new simulation. Okay. And, it has some average wind speed. Go ahead and leave these as it is. These are good averages, right? And yeah, we can basically leave all these as it is, and we go to simulate and plot. Okay. And now it gives us a choice of what we want to actually show on our plot. All right. So basically, altitude and velocity are most important, right? That's what we care about. How fast is this thing going, and what is the altitude that it's going at? So we can get rid of vertical acceleration. That's fine. And then we go ahead and we click plot. All right. Cool, right? This is really, really cool. So so over here, we look at this, we have altitude. This shows us that our rocket very, very beautifully shot up into the sky, right? It reached a height of 300 meters. That's fantastic, right? Then the parachute was deployed and it started to go down, drifting down because the parachute made it slow down, and the altitude's going down, going down, going down, going down, going down, going down, right? Cool, right? All right. Now, what is this blue thing? The blue thing is the velocity. Well, this is great. It says that at some point, it launches, the velocity increases until the motor burns out. Then it's just drifting upwards, right? So it's obviously after the motor burns, there's still a velocity, so it's still going to continue to go upward, but the velocity stops because drag now is starting to slow it down. And then at the very apogee, your recovery device is deployed, right? And now you have a constant negative velocity that's allowing this thing to slowly drift to the Earth without getting damaged, right? So this is how you have a nice stable flight. This is what a really great rocket simulation looks like. If it's weird and jagged, or the height ends up only at like 50 meters or something like that, that you've done something wrong. Okay, so you can take a screenshot of this because you're going to want to incorporate that in your lab. You click close, and so I actually wanted you guys to name this like baseline, but yeah, you can do that in the next one. So I'm going to click close. All right, now that's my baseline simulation. The rest of the lab, the final parts of the lab, you're going to do 6 more simulations, 3 of which you're changing the fins, and 3 of which you're changing anything else. It could be the shape of the nose cone, it could be the length of the body, and you want to see what maximizes the velocity and altitude of your flight. Yeah, that's essentially what you want to do. You want to see what will make this the most stable, a solid flight that goes the highest. But that also doesn't mean you need to make a short, tiny little rocket just to get a lot of height. Using this length, what will maximize the height? Okay. So also you want to make sure your center of pressure is still behind your center of gravity. It is here, so that's still going to be a stable flight. All right. Now I'm just going to show you how to edit one thing. So new simulation. Close. I'm going to go back to rocket design, and I'm going to select the body here, and I'm going to go to my fins, and I'm going to double click on that, and I'm going to change the shape of the fins, right? So instead of this, let me go more traditional, right? Almost like a more traditional thing like that. So how does changing just that affect the flight? So I'm going to click close. Now this looks much more traditional. I'm going to go back to flight simulation. I'm going to do new simulation, simulate and plot. Cool, plot. All right, what changes? Not a heck of a lot. There may be a little bit of a difference in the altitude. I think maybe actually it's a little bit less. I don't know. It's hard to tell. I would have to go back to my old graph. But now you have this ability to compare this fin shape to your previous fin shape to see if it's actually better or not. Again, you notice lovely, very smooth flight. And so now it's 2. Go ahead and take a screenshot of this. And you want to do 2 more changes to your fins. And you want to do 3 changes to anything else on this rocket to see how it affects the flight and performance. And then you're going to incorporate those 6 graphs and the table that's inside of your lab. You're going to incorporate that into your lab write up. And that's the lab this week. All right. That was a lot. That was a mouthful. But you can see it's pretty neat, pretty cool. It's drawing the line between video games and physics once again. Only thing is that this is actually going to launch in real life. Good luck, everyone.